A month ago, I started building a little jukebox that you can use with RFID. And the only thing that this jukebox was able to do is to skip to the next song or just choose the next song. And I think if I would have known Daniel earlier, it would not only be able to skip to the next song, but maybe also have volume buttons and many other things that you can do with what he's going to show you guys. Give Daniel a warm round of applause, and then we can get started.
All right, hello. Can everybody hear me well? I have to admit this is my first time talking, speaking for such a big crowd. And I'm really thankful for this opportunity to basically share my work. And I think it would make sense to get to know each other first a bit. So let me start off by a question. Who of you has programmed a microcontroller ever? Okay, great, thanks. Of those people, who of you has worked with Bluetooth Low Energy before? All right, that's 20% maybe. Last question. Who of you liked working with Bluetooth Low Energy? That is a surprising lot of people. That was too early. So I myself, I have undergone all of these three things. Basically, I have started off with wanting to build a smart home. And I have, for the first iteration, let's say, I have used Wi-Fi. But as you may know, Wi-Fi is a bit, sorry, I have to set a timer here. As you may know, Wi-Fi is a bit power hungry. So I had cables running everywhere. And then, in parallel, I'll try to turn on the video that should be playing right now, which is apparently taking a bit of time to load. But essentially, the first iteration was Wi-Fi. Cables everywhere, and I knew that something needed to change. So I started learning about Bluetooth Low Energy. Why? Because it's cheap, essentially. It's cheap. It's built into all of our phones, or most of our phones. And, well, there's a broad range of microcontrollers available, starting from the ESP32 over, let me do this manually, this is tedious. Starting from the ESP32 over like Nordic devices and TI devices and whatnot. There's plenty. And what you're seeing here is a few of my, let's call them, lovingly call them art pieces. The keys you might have noticed just spawned in the little wooden thing. That didn't really happen. I cheated a bit. But essentially you're seeing that in every task there's like movement involved. Some sort of movement. Let's play this again, please. Oh, this is, by the way, the button I'm having here as well. Right, so there's everywhere there's some sort of sensor involved and some sort of movement, or basically action and reaction. And these, I would just assume, are the tasks that most of us have to handle every now and then in some form or another. But I would say that most tasks don't really need like heavy computing or analog signals or alike. Let's try scrolling. Great. Should have tested the YouTube video, shouldn't I? Right, so moving on. If we compare all the tasks that we've just looked at, right? There was some sort of motor involved, there was some sort of sensor, and essentially it's not tricky. Everyone, and there's plenty of you who have worked with microcontrollers, you will know that reading most sensors is a matter of reading a 0 or a 1, or like a high or a low, whatnot. And controlling some mechatronics is also most of the time a matter of switching on a MOSFET, like switching on or off some MOSFET. So basically outputting a 1 or a 0 again. With motors, it might get somewhat complicated because you have like MOSFETs involved or drivers. But even for stepper motors, who of you has worked with stepper motors? Right. So if I will assume that you have used some sort of driver, like a 4988 or something, or like a TLC driver, whatever. So it's also just a matter of outputting a signal, maybe a somewhat more complicated signal. Does this work? No. Thank you. Okay, switching my slides will be tedious apparently. Ah, thanks. So if you look at the circuitry that is involved in controlling a motor, it is really nothing fancy. For the easiest part, you do have your motor that's marked by the little circle with the M. You have a MOSFET, you switch it on, and the motor runs. This is low side switching, and also do high side. There is a bit of theory involved, but essentially these are the parts. These are like the least amount of parts you need. For a BJT, you need some current limiting resistor. For a MOSFET, it is recommended to use some pull resistor for it to counter floating outputs, but essentially there's not really much to it. And I obviously discovered this myself. So having done like quite a bit of stuff with Wi-Fi, I wanted to move to Bluetooth Low Energy, to something power efficient. So it was 3 or 4 years ago, I started with a project that allows me to connect a sensor, like a reed switch mostly, or a tilt switch, or a vibration sensor. And whenever there's a sensor change, my little board, my code would basically broadcast whatever data was generated then. It was a 1 or a 0. Let's see what we have there. Yeah, that's a microcontroller. I opted for using the Nordic NRF 51, I think, 51, yes. And this should be the 51Y. It's not the cheapest. There are cheaper options, but it's either difficult to develop for them, or there's a not so good community, or they're not as power efficient. In any case, Nordic is a great choice if you want to learn, because they have a great community, they help you. There's a lot of documentation. Right, this is, maybe Bluetooth is not the best option in here. So I've just talked about my little first iteration sensor broadcasting its data. So what I had on my hands basically was some sort of a platform. It was a board that was pre-flashed. Let's say I had a dozen of those boards. All I needed to do when like deploying a new sensor was connect a sensor to it, put a battery in it, stick it somewhere, and it worked. And that was great. Having one single code base for all my sensors obviously has its benefits. And this ties neatly into the roles of Bluetooth Low Energy. We will have a bit of theory about BLE, although the whole point of this project is to not having to deal with Bluetooth Low Energy. So this is like purely educational. But essentially, my first iteration of sensor was working in a peripheral central configuration, let's call it. That means that my sensor was the peripheral, just broadcasting out data. And my center, my observer, I think they're called, it was receiving the data, as was anyone else in the around me, which might be bad security-wise. This is a fairly simple concept. You don't need to establish any connections. But the bad thing is you have no feedback. So if for whatever reason the broadcast gets lost, well, it's lost. There's no feedback. The sender doesn't know that it's lost. And also you cannot control anything. So in the peripheral central configuration, the central can't send any control sequences or control commands to the peripheral, which became a problem eventually, because I noticed that the whole Bluetooth Low Energy thing is promising. It has lots of potential, and theoretically it does support scenarios where you control stuff. My project just didn't. So I rewrote the project into something that is connection oriented. I rewrote it into something that you can connect to, and then you can read inputs and you can write outputs. But still, there was the early stage of development, and stuff like the pin configuration was hard-coded into the program. And if I needed to send out a sequence, for instance, I had to send out an impulse of, let's say, 100 milliseconds. The 100 milliseconds was also hard-coded. And when I needed a little change, I copied the code to a new version, And I did know about Git back then. I just didn't think of using it. So at the end of the day, for every application, I had basically an own code base, which was identical to all the other code bases. For like 95%, there were just minuscule changes and differences. So, right, when we speak about connection-oriented, we're still talking about centrals and peripherals. The peripherals are usually the controlled part, while the central is the controlling part. But we're talking about masters and slaves now. So the master is the one initiating the connection, and the slave is the one that is being connected to. And usually slave is the peripheral, so the one being controlled as well. Right, let's have a shallow dive into the Bluetooth Low Energy stack. I'm sure that many of you have dealt with Bluetooth before, and I'm expecting some of you to be a little bit angry because Bluetooth headphones don't work the way they have to. Same goes for mice and keyboards. But we're talking about Bluetooth Low Energy. It's a bit different. It is not meant, well, it is meant for transmitting audio, but that's a fairly recent development. Essentially, just a quick dipping our toes into the stack. We have the physical layer, which is like super duper low power, optimized for low energy consumption, differs from Bluetooth Classic. We then have the link layer. This one is responsible for establishing connections. This one is indeed responsible for the partners remembering each other. Then there's the L2 cap layer, which, as far as I understand, is comparable to, I'll call it TCP. So L2 cap, I think, is something like reliable packet transmission. So it takes care of resending packets and confirmation, etc. Then there's attributes, the attribute layer, which allows you to basically have a bunch of endpoints, right? The endpoints there is no classification yet. It's just endpoints. You can do with them whatever you want. On top of the attribute layer, there's the There's the GATT layer, right? Which structures your endpoints into services, characteristics, and descriptors. We'll take a look into those in a second. And then on top, there's the application that's controlling all the bottom layers, all the layers below it, right? The application is where your logic, or in this case, my logic resides. I think GET is generic attributes, whatever. Right, so just to let you in on what I had to suffer through, and the two people of you had to suffer through as well, probably. Developing an application that works with Bluetooth Low Energy is fairly painful. You have to learn a lot. You have to understand a lot. It personally took me years, I would say 1 or 2 years, until I started understanding what's going on and how to properly tune whatever I'm doing. Right, so you have to obviously initialize the wireless stack, which does have its caveats already. You have to differentiate whether you have a low frequency crystal or not, and so on. Right, then you have to start some timers, mostly your timers, I will admit, but usually timers are involved. You have to take care of security. That is part of stack initialization, but essentially you have to define how secure the connection is, man-in-the-middle protection, and so on and so forth. Right, then you have to register a lot of handlers. Right, a handler is a function that is getting called by someone else, in this case the Bluetooth stack. Because if you write an application, at least that's the case for the Nordic SDK. If you write an application, you have to handle all relevant Bluetooth Low Energy events. So if a connection gets established, you have to handle it. If there's some packet being sent, you have to handle that, and you have to understand if the packet is a characteristic write, a descriptor write, or whatnot. So it is tricky to take care of all the callbacks, and well, you obviously also have to handle. You not only have to set them up, you have to handle the events. Right, and then you have to set up your services, characteristics, your GATT server, which we're going to talk about in a second. And then there's the connection parameters, which by itself is a bit of magic. But it does make sense after 700 days, roundabout. Let's talk about the mystical GATT server I was talking about. So, top level of a GATT server is the GATT server, that's the root. Every GATT server has services. it can have services. It can also be empty. A service is basically a group of similar functions, right? An example would be the, is it on here? It isn't. An example would be the heart rate monitoring service. It does usually include some functionality that is grouped together by a category. Same goes for the battery service, which we do have in my project. It allows you to query different information about the battery, right? And every service contains a few characteristics. A characteristic is an endpoint. For the heart rate service, a characteristic could be the heart rate, beats per minute. Another characteristic could be the RR interval. So I think that's the interval between two heartbeats. And for the battery service, obviously, you could, for instance, read out the battery percentage, which is included in the standard. The Bluetooth special interest group made up all those specifications. And I also added the battery voltage to the battery service. I mean, I'm free to do that. I'm just not adhering to the standard then. And also there's descriptors. They're not that important for this project, but essentially descriptors are like metadata about your characteristics. So if you want to receive notifications or updates on a characteristic, if you want to get push messages, I'll call them, you have to write a special flag to the descriptor of the characteristic you're subscribing to. Whatever, let us not bother with that too much. And lastly, let's quickly talk about the Bluetooth Low Energy. Oh, it's still in German up there. Let's quickly talk about the connection parameters, which I mentioned briefly. The connection parameters, they allow you to achieve a balance of, what do you call it, of latency, of how well you can reach your peripheral, and how battery consumption. So you can configure them to be extremely latent and to be extremely quick in response, but it will consume more battery. You can also configure it to be slow, but very power efficient. How does it work? Well, thinking about it now, it's fairly intuitive. So let's imagine that, I'll take you. Let's imagine that you are my sensor, or you are a sensor, whatever. You have some data. You're a window sensor. And I'm the central interested in your data, right? So if we imagine that I ask you, hey, is the window open? You will say no, because it isn't open, right? I then ask again. You will say no again. And that happens 10 times per second. Not knowing you personally, I will just assume that you will be annoyed after 500 milliseconds, right? So at some point in time, you will tell me, you can ask as often as you want, but I will not respond to you. I will respond to you whenever there's a change. Whenever someone opened the window, then I'll tell you that, yo, now the window is open. But if there's no change, there's no point in responding. To which I will respond, true, that is, but if I constantly ask you and you don't answer, that feels a bit one-sided. Doesn't feel like a loving relationship. So I would ask you to respond to me at least every 10 seconds or so that I know you're alive, right? Just every 10 seconds tell me the window is still closed, and then I know that you're alive and we're both doing well. And this is what I tried to demonstrate here, right? So we have agreed on a 200 milliseconds interval, the connection interval, which means that the central device, or the master in this case, will send a response every 200 milliseconds. But because of the slave interval of 3, the peripheral, the slave, will only have to respond to every third request, which, as you might imagine, gives us a lot of flexibility and might save heaps of power. But in the worst case, if someone opens the window or whatever, the longest the central will have to wait is 200 milliseconds. Because let's assume that the peripheral ignores the first connection attempt, and it ignores the second. It just ignores the first, right? Then someone opens the window, and then the peripheral will know that after 150 milliseconds there will be a next connection interval. It will wake up, and then it will respond as soon as possible to the master. And this configuration, it is great for sensors, for pure sensors. So if you have something that is only delivering data to the central, then you can make it sleep for very long while still maintaining a quick response time. But if you want to control something, if you want to send control data to it, some commands, well, it's pretty bad if the thing sleeps for half a minute, right? So if you have a bi-directional connection, or even if you just want to have the controlling power over something, then you would configure it in a way where it responds to every of your requests, because you wouldn't want it to ignore your requests. So what's the takeaway here? The takeaway is Bluetooth Low Energy is fairly complicated. Starting from choosing the right hardware, to writing all the C code, to tuning your connection parameters, taking care of security, and so on. Let's see what we have in stock here. So as I mentioned earlier, as I stopped basically earlier, at one point in time I had multiple code bases with basically the same code. But one of the code bases was controlling pin 1, while the next one was controlling pin 10, doing the same thing on the pen. And the third one was outputting not 100, but 150 milliseconds onto the pin. So it was minuscule changes. And I started to think about how I could combine all of those code bases into one single reusable thing. And that is how Blenky was born, right? Blenky because it's a combination of Blinky for the thing that blinks and Bluetooth Low Energy. So what can Blenky actually do? Well, it allows you to do your GPIO configuration, which we'll take a look at. It allows you to interface with your GPIOs via Bluetooth Low Energy, which we'll also take a look at. You can compile optional features into it. Personally, I do have a little Blenky flash thing, whatever, on my bicycle that connects to my phone and records my speed and cadence, so I can check how much distance I've driven. Right, you can also tune the connection parameters, although it does it for you already. So the default configuration already looks at how many outputs, how many inputs, and tunes the connection parameters to be reasonable in my mind, right? But you can override that. And you can execute basically logic, you can execute, let's call it code, sequences, on the chip itself. That is not relevant for now. Maybe I should mention what Blenky is, right? How you could use it. Blenky is a firmware. Who of you knows Tasmota? Who of you has used Tasmota? That's more people than having used Bluetooth Low Energy, right? So Blenky is a firmware, assuming you do have the right microcontroller, which will change in the future, but for now it's limited to Nordic controllers. You could theoretically just flash Blenky onto the thing, and as of yesterday, there are instructions how to do that. And afterwards, we're at the point that we together are right now. So I do have, by luck, I do have a microcontroller with me with a battery plugged in and Blenky flashed onto it. And what I could do now, hopefully, I open a website, which I will enlarge for you. Let's make it a bit bigger. I will click on connect to device and hopefully something will show up. Although I must say that I did have a bit of issues with Bluetooth Low Energy up here. Let's make sure I have disconnected myself everywhere. Now it will show up. I have to warn you, right now this fancy Bluetooth Low Energy browser thing works with Chromium browsers. I'm sorry I have not considered that when developing this. But that's how it is right now. And already down here you will see all the available pins. From pin 0 to pin 31, all 32 pins. And we can configure them, which, I'll be honest, I have already done. So I've clicked on, I've clicked on select board, clicked on the one that looks most familiar, and there you go. There's a configuration. The thing I just chose, it knows that pin 8 is connected to a button, it knows that pin 12 is connected to an LED, and so on. And if I then send it to the device will remember the configuration and it will present to me an interface to interface with those pins via Bluetooth Low Energy. And an example of those is I'm hopefully you can see the LEDs, but if I start clicking these buttons, that was the worst button I could have chosen. But if I start clicking the buttons, hopefully most of you will see that there's something lighting up on the thing. Does anyone not see a green and a red LED? Okay, so they're bright enough. Fantastic. I also, thank you. I also have a green, well, the Chinese put a green LED on there. I didn't do that. And same goes for the digital inputs. You'll have to trust me that this is not faked, but if I press a button now, it will light up on the website. If I press another button, the other one will light up. So to summarize, the microcontroller with the Blenky flashed onto it is connected to this website via Bluetooth Low Energy. It's a standardized protocol. You can also use Python, for example, to interface with the Bluetooth Low Energy of the thing, right? But I have one last trick up my sleeve. If we recall the video I showed you, many of those tasks can already be solved by the thing we're having on the floor in the desk right now. Because many of those were about writing an output or reading an input. Nothing too tricky. And already, if this project existed when I started working with Bluetooth Low Energy, this project would have saved me years of development. But that's me. Maybe I'm just slow. But I do have one last trick up my sleeve, and that is sequences. There should be an asset down there. It's not loading. Whatever. What we can also do is we can program simple sequences through a GUI. I will, for instance, let this repeat, let's say 100 times. And the first frame will turn on second LED, the second frame will turn on the third LED, and if I now send it, you will hopefully see this blinking in police colors, which was not by... The police colors were not intentional. And you might wonder how the sequence thing was done. When I developed the sequence, I started off by thinking about a protocol. I started off by packaging those frames into like PDUs or packets and sending them over. And then I also had to somehow communicate to the thing how often this thing is supposed to blink and whatnot. And then I thought to myself, but how about reading inputs? What if we could react to inputs? Short story long, there's a new programming language now. If I, let us close all of this, we don't need this. I call the thing GPIO ASM, GPIO assembler. Why is it called like that? Because it's assembler-like, it has very few easy commands, and well, you interface with your GPIOs, right? So let's say we would wait, let's say the police colors really annoy us. We want to only blink the red color. How would it look like? I will spell you the details. We first create a label. Can everyone see that? I'll enlarge that a bit, right? We then say write digital, we ignore the first pin and write the second pin. We then say sleep ms, let's say 200 milliseconds, write digital 0, sleep ms 200 again, and then we jump to the start. Right? So I hope that this assembler code is somewhat understandable. We're basically just manipulating outputs. And then I can copy the path of this, go back to my website. That is the wrong website. Click on upload file. Voila. It will then show me what the compiled code I just wrote looks like. It will also split the code into packets in case we want to send the packets by hand. And if I then click send to device, damn it, the red is still lighting up. Let us fix that. It's still the red one. Now it's just the blue one. So what happened now? And what I can do now is I can disconnect from the thing, right? There's no connection. This thing is just going on by itself. If I click to connect to device, it will scan it again. Great. That proves nothing. This those 4 pixels. But in any case, you'll have to trust me that this thing is working autonomously on its own. It is executing our code. And if you recall the video I showed you, there's a thing opening my door, right? Do I have this somewhere? I do. Nope. Nope. Yup. So, the right picture, this is the mess that is opening my door every day. To make it short, there's a stepper motor in there. And to control the stepper motor, I have to output a pulse. I have to output 200 or so impulses, precisely timed impulses. So what I do is I have a piece of code. It says output a 1, wait for, let's say, 100 milliseconds. I output a 0, and then we say jump count start 200. Right, we save this. God damn it. We go back to the website. It just showed up. Or did any of you connect to the thing by any chance? In any case, you can play around with it. But the whole GPIO assembler thing is meant as a extension of simple 1 or 0 commands, right? Instead of sending 1010, I can just send my little packet of compiled GPIO ASM code. The thing will turn my stepper motor for exactly 200 steps. My door will open. Everyone will be happy. And right, just as a little insight, personally, I have ESP32s in every room, and those one bridge MQTT to BLE. So this allows me to talk to my Blenky microcontrollers using MQTT with like 4 euros or something per room. So this might be a consideration when you plan your infrastructure. It doesn't allow me to scroll again. And with these words, I'm saying thanks to you all. I know that what I did is there's different solutions. I want to make it as good and as useful as if possible. So if you have any suggestions, any criticisms to the whole project, I'll be more than happy to hear about them. If you want to see about my other project, as a QR code, you'll find Blenky on there. Among other things, you'll find all the stuff I've built with Blenky, and like just stupid and fun different gimmicks. And that's it from my side. Thank you.
All right. Thank you, Daniel, for this fantastic talk and going through the valley of tears for us. If there's any questions, just ask them, raise your hand, and then I will come and give you the microphone.
Hi, thanks for the talk. Do you already know or have tried to implement this in Home Assistant? Like, could we just do this, put this on a device, and then have the device show up in Home Assistant via the Bluetooth bridges?
No. This will be necessary, I fear. And I have looked into Home Assistant. I have looked into how we could interface with Blenky with whatever exists now, which would be, I think it's called you can use the ESP32 and configure it somehow to connect to the thing. But I didn't understand how you could like write data to it and read it, so it would make sense. So eventually, this will have to happen. But the protocol to interface with that is really simple. If you want to generate like GPIO ASM code, that's a bit more tricky, but still the compiler is open, should be doable. So I have thought about that, but I haven't done it yet.
Thank you.
Any other questions? Maybe from the internet? All right, if there's nobody else asking a question, I think then we can close it now. Probably Daniel will be available somewhere, maybe here, maybe at the bar, if you have further questions. And please, one more warm round of applause for Daniel.
you.